Hi, I'm Hareesh Godaba from the Center for Advanced Robotics at Queen Mary, University of London. Today I'll be talking about our work on developing a bending sensor based on upgraded optical fibers towards the challenge of soft proprioception in soft robots. In the last 2 decades or so, we have seen there is a large impetus to develop robots that are soft and much more lifelike by being inspired by the natural life all around us. So many researchers have developed these interesting robots with very interesting and peculiar deformations. So here we can see an inchworm robot that can crawl and even pass under obstacles. And here we see a very lifelike octopus-inspired robot that can gracefully swim in water. So with these developments, we're able to do more and more versatile tasks. Along with these interesting developments also come some challenges. So with the increased scope of applications and the increased demand for autonomy, we see that there is a large requirement to sensorize this type of robots. Some typical challenges are that these robots have infinite degrees of freedom. They need different type of sensing, such as proprioceptive sensors that can localize the internal states of the robot body, or also some exteroceptive sensors that can help sense external forces or external stimuli acting on this robot, and probably some other multimodal or proprioceptive sensors like IMUs, or temperature, light, humidity sensors to enable us to do various other tasks. But here for our work, we are mainly interested in these two types of sensors, which are helpful to sense internal states, such as deformations or strains, and external stimuli in a soft robot. And so for this, there are actually a large number of sensing technologies, but we are especially interested in these optoelectronic or optical fiber-based sensors because recently they have been shown that they can be easily fabricated from different widely available materials, and they can be easily integrated into soft robots. So the main principle concept in sensing using this optical waveguides is this. So these optical waveguides generally have two materials. One is the central core and the other is a surrounding cladding. The core generally is made of a high refractive index material compared to the cladding, so that when light is incident on this core of the optical fiber, the light undergoes total internal reflection, passing along the core with minimal transmission losses. However, we also know that when there is a large bending, this can cause some light loss at the core cladding interface. So some researchers have realized that by actually looking at the light loss in this optical fiber, we can actually characterize the bending in this fiber. At the same time, some deformation in the cross section of this core by other external normal forces can also cause a change in the optical intensity of the light that is transmitted to the fiber. So this can probably also be used to characterize normal forces acting on this waveguides. So by employing this principle, one of the excellent works has been in development of highly stretchable waveguides for sensorizing soft robot fingers. So here, this group from Cornell has developed waveguides made of two different types of silicones with different refractive indices, and they have been introduced into a soft robot finger to sense deformation or bending, and also external forces that have been acting on this soft robot finger. In another work, they have also used this stretchable waveguides for sensing a soft robot finger that can measure both deformation as well as forces, and they have applied that in deep sea. The hydrostatic pressures are very high. So we can see that this type of sensing modalities can also work in such extreme environments, which is very advantageous. However, some of the main ongoing challenges are that whenever these light guides based sensors are used in soft robots or soft grippers, it is very challenging to decouple the change in optical intensity that is caused by bending and which is caused by external forces. And another ongoing challenge is to develop low cost and easy to integrate solutions that can be scaled for sensorizing or to achieve distributed sensing in the soft robots. So for this challenge, we have turned to look at traditionally available optical fibers. So in the commercial simplex optic fibers, there's a single core covered by a cladding, and outside there is a plastic coating to protect this core and cladding assembly. So one of the researchers, Sina Sare, in 2015 actually looked at utilizing these simplex optical fibers. Generally, these fibers have very low transmission losses, but then at extremely high curvatures, these also have significant transmission losses that can be recorded by an optical amplifier. So what Sina Sare did is that they made the sensor into this high curvature shape, and now when there is a change in this curvature because of stretching of this actuator or because of stretching of this fiber, that can result in change in in the transmission loss, which can be used to detect stretching or apply two of these macro bend stretch sensors to characterize bending in a soft actuator. So we try to see if there are other ways in which we can make these commercial optical fibers very sensitive to bending, so that we do not need to use this high curvature type sensors which can only detect stretch when they're used alone. So what we did was we tried to make use of this principle of surface scattering. So we remove the plastic sheath on the top of this simplex optic fiber, and then which exposes the cladding, and then we abrade this cladding with a rough surface. So what happens is that the surface now becomes rough, and so any light incident has higher optical losses. So even without a very high curvature, this type of optical fiber can now have higher optical losses. So any change in any change in curvature can increase this optical loss, which can be noted by an optical fiber and help us to develop a deformation sensor. So we also cast silicone around it to give it some structural rigidity, and so that we can also employ it in a soft robot finger. So here you can see that when light is incident to the optical fiber, some of it escapes through this silicone material or from this core through the cladding into this silicone material. And when there's deformation, we can note by using a simple optical amplifier to see what is the change in this transmission loss. Since we're also interested in the force response of these sensors, we have made a stretchable light guide composed of two silicones by following some techniques in the literature and fabricate the stretchable sensor. We then tested the sensor response to bending for both this abraded fiber-based sensor and silicone-based sensor. We see that both of them are responsive to bending, although probably the range of curvature for the abraded fiber-based sensor can be slightly higher compared to the silicone-based sensor. Now we put both these sensors to a compression test. So we put this sensor on a universal testing machine and apply compression normally on the surface to achieve a fixed amount of deformation. Since the sensitivities of these two sensors are not the same, we normalize them by dividing the sensor value change due to compression by the sensor value change when the sensors are wrapped around a cylinder of diameter 5 centimeter, which is close to the saturation region for both these sensors. So here you can say we have delta sensor value divided by delta sensor value 2.5, which is compared for both these. So in silicone-based sensor, when there is compression, the sensor reading decreases as expected. However, for the abraded fiber sensor, surprisingly, we've seen that the sensor reading actually increases. This may be because of some interface effects between this rough cladding surface and the surrounding silicone medium that this fiber is encompassed in. Now, coming to this difference in the force sensitivities, we see that for the abraded fiber sensor, at a force of almost 120 Newton, we see that this change in this ratio is less than 0.03. However, for silicon-based sensor, for a force of just 50 to 60 Newton, the change in this ratio is around 0.04. So we can understand that the abraded fiber-based sensor is actually much less sensitive to applied normal pressures. So with this, we take and apply this abraded fiber sensor to a soft pneumatic finger. So we fabricated a soft pneumatic finger with a traditional unit structure that is in the literature, and we embedded this bending sensor at the at the at the bottom surface of this of this soft pneumatic finger, and we connect this to a Keynes optical amplifier, which is then connected to a data acquisition card. So now when we actuate this finger or this soft robotic finger, the deformation causes a change in the optical intensity transmitted through this bending sensor, which is noted as a voltage. So now we program different levels of applied pressure to this finger. So we go from 0 all the way to 13 psi, and then we also record the sensor reading, which is shown in red here. Then we have taken images of this soft robotic finger, and then calculate the curvature by some image processing technique, and then we develop a calibration curve that maps the sensor reading to the curvature of the finger. So here is a video showing this finger embedded with a sensor. So as we apply the pressure, we can see that the finger begins to actuate, and here we see the sensor reading in this, that is shown as this white line changing with time. You can see that the sensor is quite responsive to changes in deformation, and we can even see some small transients as the sensor vibrates, although there is scope for improvement in the level of this minute deformations. So in conclusion, we have developed bending sensors which are based on low-cost commercial optical fibers, and we also see that these are relatively insensitive to pressure. Then we have taken and applied the sensor to sense bending in a soft pneumatic finger. In future work, we plan to investigate the effect of this adjoining media on the force and bending response of the sensor, because we think that the color or the type of this silicone has a significant effect on the sensor response of this abraded fiber optic sensor. Then in our current work, we are actually looking at a combined application of silicone-based soft sensor and this abraded fiber sensor to see if we can use this abraded fiber-based sensor as a reference for the bending deformation, and then use the silicone-based sensor to actually measure or calculate the forces that are being applied. And in further work, we're also looking at scaling the number of these abraded fiber sensors along the length of a finger so that we can achieve distributed sensing. These sensors are only about 1 millimeter in diameter, so a large number of them with the active regions in different points along the length of the soft robotic gripper can be used to achieve distributed sensing in soft robot grippers. So thank you very much. And you can direct any comments or questions to my email shown here. Thank you.